So here's something worth thinking about as you settle in tonight. Right now, wherever you are, you're being held together. Not in some vague, poetic sense. I mean literally, physically, at every single scale of your existence. Something is doing the work of keeping things from flying apart. The atoms in your bones aren't drifting away from each other. The floor beneath your bed isn't sinking into the earth. The earth itself isn't crumbling into dust. And if you zoom way, way out, the galaxy you're sitting in right now is spinning in a structure so vast it takes light itself 100,000 years just to cross it. And even that enormous pinwheel is holding together, bound by something invisible and persistent, and honestly, kind of miraculous when you stop to really think about it. So tonight, that's what we're going to do. We're going to think about it. Slowly, gently, one layer at a time. We're going to talk about what holds reality together, from the smallest things we know about, all the way up to the largest structures in the universe, and everything in between. How your coffee mug is solid, why bridges don't collapse, what actually happens inside a star, why you can lean against a wall and the wall pushes back. And we're going to do it by following the story of how people figured all of this out. Because that story is full of real humans doing extraordinary things, getting things wrong, arguing with each other, and occasionally stumbling onto truths so deep they change the way our entire species understands existence. You don't need to stay awake for all of it. That's the whole point. Just let it wash over you, and wherever you drift off, that's exactly the right place. Let's start where it makes sense to start. With the oldest question. What is stuff made of? What's the nature of the material world? Because that's really the first version of our question. Before you can ask what holds things together, you have to ask what things even are. And the first people we know of who took a serious crack at this lived in a world that, honestly, must have felt deeply mysterious. Imagine being alive in ancient Greece, around the 5th or 6th century before the Common Era. You've got no microscopes, no telescopes, no particle accelerators. You've got your eyes, your hands, fire, water, rocks, wood, and your own relentless curiosity. And somehow, from that starting position, a handful of thinkers in the Eastern Mediterranean began asking questions that wouldn't be fully answered for another 2,500 years. There was Thales of Miletus, working around 585 BCE, who's often called the first philosopher of nature. His big idea was that everything, all of it, every rock and river and living creature, was ultimately made of water. Now that sounds almost charmingly wrong to us, but think about what he was actually doing. He was saying that beneath the apparent chaos and variety of the world, there's one underlying substance, one thing that takes different forms. That's a radical idea. That's the seed of everything that comes after. Then came Anaximenes, who thought it was air, Heraclitus, who favored fire, Empedocles, who kind of split the difference and said there were 4 fundamental elements: earth, water, air, and fire, and that everything you see is just different mixtures of those 4. And look, from a modern perspective, the specific answers were wrong. But the question they were asking? That question was exactly right. What are the basic building blocks, and how do they combine to make the world we experience? And then, around 460 BCE or so, something really remarkable happens. A man named Democritus, building on ideas from his teacher Leucippus, proposes something astonishing. He says that if you take any piece of matter, a chunk of iron, a piece of bread, anything, and you keep cutting it in half, and in half again, and in half again, eventually you'll reach a piece so small it can't be cut anymore. He calls this piece atomos, uncuttable. The atom, Now, Democritus couldn't prove this. He had no way to test it. It was pure reasoning, pure intuition. But here's what's wild. He was essentially right. Not in every detail, obviously. The atoms we know about today are far stranger and more complex than anything Democritus imagined. But the core insight, that matter is not infinitely divisible, that there are fundamental discrete units that make up everything, that idea would turn out to be one of the most important ideas any human being has ever had. The thing is, not everyone bought it. In fact, the most influential thinker of the ancient world, Aristotle, rejected atomism. Aristotle, who was born in 384 BCE and whose ideas would dominate Western thought for nearly 2 millennia, preferred a continuous model of matter. He kept the 4 elements of Empedocles and added a 5th, ether, the stuff of the heavens. And because Aristotle was Aristotle, because his authority was so towering, the atomic idea got kind of shelved for a very long time. We're talking centuries. More than a millennium, really. And that's worth sitting with for a moment, because it tells you something important about how knowledge works. The right idea can exist and still lose. It can be proposed, make perfect sense, and then get buried under the weight of authority and tradition. Democritus was right, and it didn't matter. Not for a very, very long time. So let's jump forward. Let's skip past the Roman period, past the medieval era, past 1,000 years of alchemy and speculation, and land in the 17th century, when things start to change in a serious way. Because this is when people stop just thinking about what stuff is made of and start actually testing it. Start measuring. Start building instruments that let them see what their eyes alone never could. One of the key figures here is Robert Boyle, an Anglo-Irish natural philosopher born in 1627. Boyle is sometimes called the father of modern chemistry, and one of the things he did was take a hard look at the old idea of 4 elements and say, essentially, this doesn't hold up. In his 1661 book, The Skeptical Chymist, he argued that elements should be defined not by ancient tradition, but by experiment. An element is a substance that can't be broken down into anything simpler. That sounds obvious now, but at the time, it was a genuinely radical reframing. Boyle also did beautiful work on gases. You might remember Boyle's law from school, the one that says if you compress a gas, its pressure goes up in proportion to how much you squeeze it. Pressure times volume equals a constant, as long as the temperature stays the same. And here's the thing about Boyle's law that matters for our story. It makes a lot more sense if you think of a gas as being made of tiny particles bouncing around. If the gas is a bunch of little things flying around in a container, then when you make the container smaller, they hit the walls more often, and you get higher pressure. Boyle himself thought in terms of particles, tiny, spring-like corpuscles, he called them. The atomic idea was creeping back. But the person who really nailed it down, who took atomism from a philosophical hunch to a scientific theory with real predictive power, was John Dalton. And Dalton's story is one of those beautiful examples of someone coming at a huge problem from an unexpected angle. Dalton was born in 1766 in Eaglesfield, a tiny village in the English Lake District. His family were Quakers, not wealthy, and he started teaching at a local school when he was just 12 years old. 12. Think about that. He was largely self-taught in science, deeply interested in meteorology and the behavior of gases, and he spent years carefully measuring how gases mixed together, how they absorbed water, how their properties changed with temperature and pressure. And it was through this painstaking work with gases that Dalton arrived at his atomic theory, which he began presenting around 1803. His key insights were these. Each chemical element is made of identical atoms. Atoms of different elements have different weights. Chemical compounds are formed when atoms of different elements combine in simple, fixed ratios. And in any chemical reaction, atoms aren't created or destroyed. They're just rearranged. This was huge. This was the moment where the atom went from being a philosophical idea to being a working scientific concept that could explain and predict real chemical behavior. Why does water always have the same composition? Because it's always two hydrogen atoms bonded to one oxygen atom. Why do chemicals combine in definite proportions? Because atoms are discrete units that join in whole number ratios. Dalton even created a system of symbols for different atoms, little circles with different markings, and started working out their relative weights. Now, Dalton got some things wrong. He assumed, for instance, that the simplest compound of two elements would be one atom of each. So he thought water was one hydrogen and one oxygen, HO, rather than H2O. It took decades of further work by people like Avogadro and Cannizzaro to sort out those ratios. But the framework was right. The architecture of the idea was sound. And here's what I want you to notice, because it's going to matter as we go deeper tonight. At this point in the story, around the early 1800s, people have figured out that matter is made of atoms. They're starting to catalog the elements, figure out their weights, understand how they combine. But they have absolutely no idea what holds them together. They know atoms exist. They know atoms form bonds. But what is a bond? What is the force that makes two hydrogen atoms stick to an oxygen atom and form water? What is the glue? That question, what is the glue, is really the beating heart of everything we're going to explore tonight. Because it turns out there isn't just one glue. There are several. And they operate at different scales, in different ways, with different strengths. And understanding them requires peeling back layer after layer of reality until you get to places that are genuinely strange. Places where your everyday intuitions about how things work just stop applying. But before we can get there, something else needs to happen in our story. Because in the early 19th century, at the same time that Dalton is working out his atomic theory, another thread of investigation is unfolding. One that seems completely unrelated at first, but turns out to be deeply, fundamentally connected. And that thread involves a force that people had known about for centuries, but never really understood. Electricity. Or more precisely, the relationship between electricity and magnetism, and the way that relationship reveals something profound about the nature of forces themselves. The story of electromagnetism is one of the great detective stories in all of science, and it starts with odd little observations that don't seem to mean much at first. People in the ancient world knew that if you rubbed amber with fur, it could attract small objects, bits of straw, feathers. The Greek word for amber, by the way, is electron, which is where we get the word electricity. And people knew about lodestones, naturally magnetic rocks that could attract iron and point north. But for most of human history, these were curiosities, party tricks. Nobody understood what they were or how they connected to anything else. That started to change in the late 18th and early 19th centuries, and the person who kicked things off in a dramatic way was an Italian physician named Luigi Galvani. In 1780, Galvani was dissecting a frog in his laboratory in Bologna when he noticed something startling. When a metal scalpel touched the frog's leg near a nerve, the leg twitched. The frog was dead. There was no life force animating it. But something was making those muscles contract. Galvani thought he'd discovered a form of electricity inherent to living tissue, which he called animal electricity. His contemporary Alessandro Volta disagreed. Volta, a physicist from Como, argued that the electricity wasn't coming from the frog. It was coming from the contact between two different metals in the presence of moisture. And to prove his point, in 1800, Volta built something extraordinary. He stacked alternating discs of zinc and copper, separated by pieces of cardboard soaked in salt water, and from this simple pile, literally called a voltaic pile, he produced a steady, continuous flow of electric current. The first battery, the first reliable source of sustained electricity. And that changed everything, because now, for the first time, scientists had a tool. They could produce electricity on demand, run it through wires and see what it did. And what it did turned out to be far more interesting than anyone expected. In 1820, a Danish physicist named Hans Christian Ørsted was giving a lecture demonstration, just a routine class, nothing special, when he noticed that a compass needle sitting near a wire deflected every time he turned on the electric current. Electricity was creating magnetism. These two forces, which everyone had assumed were completely separate phenomena, were connected. That single observation, made almost by accident during a lecture in Copenhagen, set off a chain of discoveries that would ultimately reveal one of the four fundamental forces of nature, the force that, as it turns out, is responsible for almost everything you experience in daily life. The solidity of your floor, the chemistry of your body, the light entering your eyes, the signal traveling through your phone. All of it, one force hiding in plain sight for all of human history. And it took a twitching frog leg and a compass needle to start pulling back the curtain. The person who pulled it back the furthest, at least in that era, was someone you've almost certainly heard of, but whose story is so improbable, so unlikely, that it almost sounds made up. His name was Michael Faraday, and he was born in 1791 in Newington Butts, a rough neighborhood in South London, to a family that had almost nothing. His father was a blacksmith who was frequently too ill to work. Faraday received only the most basic education. At 14, he was apprenticed to a bookbinder, and that, by every reasonable expectation, should have been the end of the story. A working-class kid in Georgian England, bound for a trade, invisible to history. But Faraday read the books he was binding. He read everything, and one of the books that fell into his hands was a popular introduction to chemistry, and something in it lit a fire in him that never went out. He started attending public lectures at the Royal Institution, which was one of those wonderful quirks of London at the time, a place where the public could actually go and hear leading scientists talk about their work. Faraday scraped together the shilling for admission, and he sat in the back, and he took meticulous notes. Not just scribbles, but beautifully organized, carefully illustrated notes that he later bound himself. Because of course he did. He was a bookbinder. And the lecturer who captivated him most was Humphrey Davy, one of the most famous chemists in England, a man who had isolated sodium and potassium and barium, and who had a flair for the dramatic that made his lectures wildly popular. Faraday took his bound notes and sent them to Davy with a letter asking for any kind of job, any position at all, in the world of science. And Davy, to his credit, was impressed enough to hire Faraday as his laboratory assistant in 1813. Now, think about what that means. A 21-year-old with no formal education, no university training, no connections, walks into one of the most prestigious scientific institutions in the world because he bound a really good set of lecture notes. It's one of those stories that reminds you how much of history turns on small, improbable moments. If Faraday had been apprenticed to a different trade, if he hadn't picked up that particular chemistry book, if Davy had tossed his letter in the bin, we might have been decades behind in understanding the force that literally holds your body together. Faraday started as essentially a servant. He cleaned glassware. He prepared chemicals. He accompanied Davy on a long tour of Europe as a combination of assistant and valet. And Davy's wife apparently treated him terribly during that trip, making it clear she considered him beneath her. But Faraday endured it because he was learning. He was watching one of the best experimentalists in the world work, and he was absorbing everything. And when they returned to London, Faraday began conducting his own experiments, quietly at first, then with increasing ambition and skill. Here's the thing about Faraday that made him different from almost every other scientist of his era. He had no mathematical training. None. He couldn't write equations. He couldn't do calculus. In a field that was becoming increasingly mathematical, Faraday thought in pictures. He thought in spatial relationships and physical intuitions. And this apparent limitation turned out to be one of the greatest advantages in the history of physics, because it forced him to develop a completely new way of thinking about forces, a way that would eventually become the foundation of all modern physics. But let's not jump ahead. Let's stay with Faraday in the early 1820s, because that's when the first breakthrough came. Remember Ørsted's discovery, that an electric current creates a magnetic effect around it? Scientists across Europe were trying to figure out what to do with that information. The French physicist André-Marie Ampère was working out the mathematics, showing that parallel wires carrying current attract or repel each other, essentially proving that magnetism could be created purely by moving electric charges. But Faraday, thinking in his visual, spatial way, asked a different kind of question. If a current-carrying wire produces a magnetic force that wraps around it in a circle, and he knew this from the way compass needles behaved near wires, then could he make something move continuously in a circle using that force? In 1821, he built a simple but ingenious device. Picture this: a bowl of mercury with a permanent magnet sticking up out of it, and a wire dangling down into the mercury so it could swing freely. When he sent current through the wire began to rotate around the magnet in a continuous circle. It sounds almost too simple, but think about what he'd actually done. He'd converted electrical energy into continuous mechanical motion. He'd built the first electric motor. It was crude. It was a laboratory curiosity. It couldn't do useful work. But the principle was there. The principle that today spins every electric fan, every washing machine drum, every Tesla on the highway, every hard drive that ever stored a file. That principle came from a bookbinder's apprentice with no mathematical training, working in a basement laboratory in London. And here's where the story takes a darker turn for a moment, because Davy, Faraday's mentor, the man who'd given him his chance, became jealous. There's some debate among historians about exactly how petty it got, but it's clear that Davy felt threatened by his protégé's rising reputation. When Faraday was nominated for fellowship in the Royal Society in 1824, Davy reportedly opposed it. The student was surpassing the teacher, and the teacher didn't handle it gracefully. Faraday was elected anyway, and Davy died a few years later, and the whole episode is a reminder that science is done by human beings with human egos, and sometimes the politics of discovery are as complicated as the discoveries themselves. But anyway, the point is this: Faraday had shown that electricity could produce motion through magnetism, the obvious next question. And Faraday was obsessed with symmetry, with the idea that nature's forces should be reciprocal, was whether it worked the other way around. if electricity creates magnetism, does magnetism create electricity? He spent nearly 10 years wrestling with this question. 10 years. He tried experiment after experiment, and most of them failed. He'd wrap wire around a magnet and look for current, and nothing would happen. It was maddening, because he was so sure the symmetry had to be there. And then, on August 29th, 1831, he finally cracked it. He wound 2 separate coils of wire around an iron ring. Imagine a donut shape made of iron, with wire wrapped around one side and a different wire wrapped around the other side. When he connected one coil to a battery, he saw a brief flicker of current in the other coil, just for an instant, right at the moment he turned the battery on, and another flicker, in the opposite direction, when he turned it off. Nothing in between, only during the change. This was the key insight, and it's so important that I want you to really sit with it for a moment. A steady magnetic field does nothing. A changing magnetic field creates electricity. It's the change that matters. Motion, variation, flux. That's what bridges the gap between magnetism and electricity. Faraday went on to demonstrate this more dramatically by simply pushing a bar magnet in and out of a coil of wire and showing that it generated a current each time the magnet moved. Move the magnet in, current flows one way. Pull it out, current flows the other way. Stop moving, current stops. This is electromagnetic induction, and it is, without exaggeration, the principle that powers civilization. Every generator in every power plant on Earth, coal, gas, nuclear, hydro, wind, works on this principle. You spin a magnet near a coil of wire, or spin a coil of wire near a magnet, and out comes electricity. The turbines are just ways of spinning things. The steam from boiling water, the falling water of a dam, the wind pushing a blade, all of it is just different ways of creating the motion that Faraday showed was necessary to coax electricity out of magnetism. So, think about your life right now. The electricity flowing through whatever device you might be listening to. This on, it was generated by electromagnetic induction, the principle discovered by a self-taught bookbinder in 1831. That's not a metaphor. That's literally the mechanism. Somewhere, right now, a coil of wire is spinning inside a magnetic field, and electrons are being pushed through copper cables, through transformers, through the grid, into your wall, into your device. Faraday's discovery, running continuously, everywhere, all the time. But Faraday wasn't done. And this is where his lack of mathematical training became, paradoxically, his greatest gift. Because he couldn't describe electromagnetic forces with equations, he developed a visual language instead. He imagined what he called lines of force, invisible lines radiating out from magnets and electric charges, filling the space around them, curving and bending and interacting. If you've ever sprinkled iron filings on a piece of paper over a magnet and seen those beautiful curved patterns, you've seen what Faraday was imagining. He believed those lines were real, that they represented something physical happening in the space itself, not just a mathematical convenience. Most physicists of his time thought this was a bit naive. The prevailing view, going back to Newton, was that forces acted at a distance, instantaneously, across empty space, with nothing in between. Gravity pulled the Earth toward the sun through a void. Magnets attracted iron across empty air. There was no need for anything to exist in the space between objects. But Faraday couldn't accept that. His intuition, honed by years of watching experiments, told him that the space around magnets and charges was doing something, that it was filled with a kind of tension, a stored energy, a physical state that he called a field. And he was right. He was profoundly, fundamentally right, in a way that would take decades for the rest of physics to fully appreciate. The concept of the field, the idea that forces aren't just things that happen between objects, but are properties of space itself, is arguably the single most important conceptual breakthrough in the history of physics. It's the idea that makes everything else possible. Quantum mechanics, general relativity, the standard model of particle physics, all of them are field theories. They all describe reality as fields permeating space, interacting, vibrating, giving rise to everything we observe. And it started with a man who couldn't do calculus, drawing imaginary lines around magnets in a London laboratory. Now, Faraday could see the lines. He could feel the physics, but he couldn't write it down in the language that other physicists demanded, mathematics. For that, the world needed someone else, someone who could take Faraday's physical intuitions and translate them into precise, rigorous equations. And that someone was born in Edinburgh, Scotland, in 1831. The very same year Faraday discovered electromagnetic induction, which is one of those coincidences that almost feels like the universe has a sense of narrative timing. His name was James Clerk Maxwell, and if Faraday was the person who saw the truth about electromagnetism, Maxwell was the person who proved it, who took those invisible lines of force, those shimmering patterns in iron filings, and carved them into the bedrock of mathematical physics so deeply that they've never been dislodged. Maxwell's story is one of those quiet, almost heartbreaking tales of genius that doesn't get told nearly enough. He wasn't a showman. He wasn't a public figure the way Faraday was. He didn't have Faraday's gift for demonstration or his flair for making science accessible to packed lecture halls. Maxwell was, in many ways, the opposite, a deeply private, gentle, somewhat eccentric Scottish physicist who did his most revolutionary work in relative obscurity and died so young that the full impact of what he'd done wasn't really understood until after he was gone. Einstein kept a photograph of Maxwell on his study wall. That tells you something. When the person widely regarded as the greatest physicist of the 20th century puts your picture on his wall, you've done something extraordinary. Maxwell grew up on a country estate in southwestern Scotland called Glenlair. His family was well off, comfortable gentry, not aristocracy, but educated and curious. His mother died when he was 8, which was devastating, and he was raised largely by his father, a warm but somewhat unconventional man who encouraged young James's relentless curiosity about how things worked. And Maxwell was curious about everything. As a child, he would ask, "What's the go of that?" about anything he encountered: a mechanical toy, a reflection in water, a beetle crossing a path. What's the go of it? What makes it work? His father would try to explain, and when the explanation wasn't satisfying enough, Maxwell would follow up with, "But what's the particular go of it?" He wanted the mechanism, the specific, precise, underlying reason. He was sent to the Edinburgh Academy as a boy, where his rural manners and homemade clothes earned him the nickname Dafty from the other students. He didn't fit in socially, not at first, but his mathematical talent was obvious almost immediately. By the age of 14, he had written a paper on the geometry of oval curves that was presented to the Royal Society of Edinburgh. He was too young to present it himself. An adult had to read it on his behalf. Think about that. A teenager producing original mathematical research that professional mathematicians found worthy of attention. And this was just the beginning. He went on to the University of Edinburgh and then to Cambridge, where he studied at Trinity College and later became a fellow at Peterhouse. At Cambridge, he was immersed in the British tradition of mathematical physics, a tradition that prized elegant equations and rigorous proofs. And this is where the timing becomes so beautiful, because Maxwell arrived at Cambridge already fascinated by electricity and magnetism, already aware of Faraday's work, and already convinced that Faraday's field concept was not just a useful visualization, but a deep physical truth that deserved a proper mathematical framework. Here's what you have to understand about the state of electromagnetic theory in the 1850s. There were equations, sure. Coulomb had his law for the force between charges. Ampere had worked out the mathematics of forces between current-carrying wires. There were various formulas floating around for different electromagnetic phenomena, but they were disconnected. They were like individual puzzle pieces scattered across a table, each one correct in its own domain, but nobody had assembled them into a coherent picture. Nobody had shown that electricity, magnetism, electromagnetic induction, and the behavior of light were all manifestations of the same underlying reality. That's what Maxwell did. And the way he did it is genuinely one of the most beautiful intellectual achievements in human history. He started in 1855, when he was just 24, with a paper called On Faraday's Lines of Force. And what he did in that paper was remarkable. He took Faraday's visual, intuitive concept of lines of force and showed that you could describe them mathematically using the same equations that govern the flow of an incompressible fluid through a porous medium. He wasn't saying that electromagnetic fields literally are fluids. He was using an analogy, a mathematical analogy, to show that Faraday's picture could be made rigorous. The lines of force behaved like streamlines in a flowing fluid. Places where the lines bunched together corresponded to stronger fields, just as places where streamlines converge correspond to faster flow. It was a translation exercise, in a sense, taking Faraday's language and rendering it in mathematics. But Maxwell wasn't done, not even close. Over the next decade, he kept pushing deeper. In 1861 and 1862, he published a much more ambitious work called On Physical Lines of Force, where he tried to build a mechanical model of the electromagnetic field. And this is where it gets wonderfully weird, because Maxwell imagined space as being filled with tiny rotating vortices, little spinning cells, with even tinier idle wheels between them to keep everything meshing together. It sounds bizarre, and honestly, it kind of was. Even Maxwell himself wasn't fully committed to the model as a literal description of reality. But here's the thing. The model worked. When he cranked through the mathematics of his spinning vortices, the equations he got out matched the known laws of electricity and magnetism. And then something completely unexpected fell out of the math. This is the moment. This is the moment that changes everything, and I want you to really sit with it, because it's one of those rare instances where a human being, sitting alone with pen and paper, discovers something about the universe that nobody had ever suspected. Maxwell found that his equations predicted the existence of waves, disturbances that would ripple through the electromagnetic field, propagating outward from their source. Waves made of oscillating electric and magnetic fields, each one generating the other in a self-sustaining dance. An electric field changing in time would create a magnetic field. That magnetic field, itself changing, would create a new electric field, and so on, leapfrogging through space, carrying energy with them. And when Maxwell calculated the speed at which these waves would travel, using only the known constants of electricity and magnetism, numbers that had been measured in laboratories using coils and capacitors and galvanometers, numbers that had nothing obvious to do with light. The answer he got was approximately 310,000 kilometers per second, the speed of light. Let that sink in for a moment. The speed of light had been measured by astronomers. The electrical and magnetic constants had been measured by physicists in completely different experiments. And when Maxwell combined those constants in his equations, out popped the speed of light. He wrote, in what might be the most understated revolutionary statement in the history of science, we can scarcely avoid the inference that light consists in the transverse undulations of the same medium which is the cause of electric and magnetic phenomena. Light is an electromagnetic wave. That's what Maxwell discovered. The light streaming through your window, the warmth of a campfire on your face, the colors of a sunset, the signal carrying your favorite song from a radio tower to your car, all of it is the same thing. Oscillating electric and magnetic fields, propagating through space at 299,792 kilometers per second. The rainbow and the radio signal, and the X-ray and the microwave heating your leftovers. They're all electromagnetic waves, differing only in their wavelength and frequency. Maxwell unified not just electricity and magnetism, but light itself into a single theoretical framework. Three seemingly separate domains of physics, electricity, magnetism, and optics, revealed to be aspects of one phenomenon. And he did all of this before anyone had ever detected an electromagnetic wave in a laboratory. That wouldn't happen until 1887, when Heinrich Hertz, a German physicist working in Karlsruhe, built an apparatus that could generate and detect radio waves, electromagnetic waves with wavelengths much longer than visible light. Hertz used a spark gap transmitter, essentially creating a rapid oscillation of electric charge that radiated electromagnetic waves outward, and then detected those waves with a simple loop of wire across the room, where tiny sparks would appear in response to the incoming radiation. It was direct physical confirmation that Maxwell's theoretical prediction was real. Electromagnetic waves existed. They traveled at the speed of light. They behaved exactly as Maxwell's equations said they should. Tragically, Maxwell didn't live to see it. He died in 1879 at the age of 48 of abdominal cancer, the same disease that had killed his mother at almost the same age. He was still working, still thinking, still asking, what's the particular go of it, right up to the end? Hertz's confirmation came 8 years after Maxwell's death, and Hertz himself died young, at 36, of a condition that today would likely be treatable. The history of physics is littered with these losses, these brilliant minds extinguished before they could see the full flowering of their ideas. But Maxwell's equations endured. In their final polished form, the form we use today, cleaned up and streamlined by Oliver Heaviside in the 1880s, there are 4 of them. Just 4 compact equations that describe all of classical electromagnetism. Every electromagnetic phenomenon you've ever encountered, from the static cling of laundry to the operation of an MRI machine to the transmission of data through fiber optic cables, is governed by those 4 equations. They tell you how electric charges create electric fields. They tell you that there are no magnetic charges, no magnetic monopoles, no isolated north or south poles. They tell you that changing magnetic fields create electric fields, which is Faraday's law of induction. And they tell you that magnetic fields are created both by electric currents and by changing electric fields. That last part, the changing electric field contribution, was Maxwell's own addition, his great theoretical leap, the term that made the equations self-consistent and made electromagnetic waves possible. Now, here's something worth pausing on. because it connects back to the deepest question we've been circling around this whole time. The question of what holds reality together. Maxwell's equations describe fields, continuous, smooth, infinitely divisible fields that permeate all of space. And for a while, in the late 19th century, it seemed like physics was nearly complete. You had Newton's mechanics describing how objects move. You had Maxwell's equations describing electricity, magnetism, and light. You had thermodynamics describing heat and energy. The pieces seemed to fit together into a tidy, elegant picture of a clockwork universe. There were a few loose ends, sure, some puzzling experimental results that didn't quite match the predictions. But most physicists assumed those would be sorted out with a little more work. They were wrong. Those loose ends were not minor imperfections in an otherwise complete tapestry. They were threads that, when pulled, would unravel the entire fabric of classical physics and reveal something far stranger, far more beautiful, and far more unsettling underneath. And the first thread to be pulled, the one that started the whole unraveling, had to do with something deceptively simple. It had to do with the color of hot objects. You've seen this yourself, even if you've never thought about it in these terms. Heat a piece of metal, and it starts to glow. First a dull red, then orange, then yellow, then white as it gets hotter. The color of the glow is related to the temperature. This was well known by the late 1800s, and physicists had been trying to derive a mathematical formula that would predict exactly how much light a hot object emits at each wavelength for any given temperature. The object they studied was an idealized one called a blackbody, a perfect absorber and emitter of radiation, something that doesn't reflect anything but radiates energy purely based on its temperature. And when they tried to use classical physics, Maxwell's electromagnetic theory combined with the statistical mechanics of Ludwig Boltzmann to predict the blackbody radiation spectrum, they got an answer that worked beautifully for long wavelengths, but went catastrophically wrong for short ones. The classical prediction said that as you moved to shorter and shorter wavelengths, toward ultraviolet light and beyond, the amount of energy radiated should increase without limit, shooting off toward infinity. This was obviously physically absurd. A hot oven does not emit infinite ultraviolet radiation. You would not be killed by opening your oven door. The prediction was so dramatically wrong that it earned a dramatic name, the ultraviolet catastrophe. And it was in the attempt to fix this catastrophe that a quiet, conservative, deeply reluctant German physicist named Max Planck did something that he himself didn't fully understand at the time, something he later described as an act of desperation. In the year 1900, on the very threshold of a new century, Planck proposed that energy is not emitted continuously, the way classical physics assumed, but in discrete little packets, tiny, indivisible bundles that he called quanta. The energy of each quantum was proportional to the frequency of the radiation, connected by a new fundamental constant that we now call Planck's constant, a number so small it's almost absurd, 6.626 times 10 to the negative 34 joule seconds. A number so tiny that in everyday life, the graininess of energy is completely invisible. But at the atomic scale, it changes everything. That tiny number, that almost comically small constant, draws a line between the world you can see and the world you can't. Above a certain scale, energy looks perfectly smooth, perfectly continuous, like water flowing from a tap. But down at the scale of atoms and photons, energy comes in lumps. It's grainy. It's countable. And once you accept that, once you really sit with what that means, the whole foundation of classical physics starts to shift beneath your feet. Now here's what's important to understand about Planck himself. He didn't set out to revolutionize physics. He wasn't some young firebrand looking to tear down the establishment. He was 42 years old in 1900, a respected professor in Berlin, a man who loved thermodynamics the way some people love gardening, carefully, methodically, with deep satisfaction in getting things exactly right. He was, by temperament, a conservative thinker. He believed in the existing laws of physics. He trusted them. And when he introduced this idea of energy quanta, he thought of it as a mathematical trick, a clever workaround to make the equations behave, not a statement about how nature actually works. He assumed that someone, eventually, would find a way to derive the same result using purely classical reasoning, and the quanta would turn out to be a convenient fiction. That never happened. Instead, the opposite happened. The quanta turned out to be more real than anyone, including Planck, was prepared for. And the person who made that clear, the person who took Planck's reluctant little trick and turned it into a genuine revolution, was a 26-year-old patent clerk in Bern, Switzerland, who in 1905 was about to have the single most extraordinary year any scientist has ever had. You know his name. Everyone knows his name. Albert Einstein. And the thing most people associate with Einstein is relativity. E equals mc squared, curved space-time, all of that. We'll get there, I promise. But here's what's fascinating. The paper that actually won Einstein his Nobel Prize wasn't about relativity at all. It was about light. Specifically, it was about something called the photoelectric effect, and it's the paper that took Planck's quanta from a mathematical convenience to a physical reality. So let's talk about the photoelectric effect, because it's one of those things that seems simple on the surface, but cracks the whole world open when you look closely. Here's the setup. If you shine light on certain metals, electrons get knocked loose from the surface. That's it. Light hits metal, electrons come out. This had been observed experimentally. Heinrich Hertz himself noticed it back in 1887, the same year he confirmed electromagnetic waves. Philipp Lenard did careful experiments on it around 1902. And the results were deeply strange. Classical physics, Maxwell's beautiful wave theory of light, predicted that the energy of the ejected electrons should depend on the intensity of the light. Brighter light means a stronger electromagnetic wave, means more energy delivered to the surface, means electrons should come flying out with more speed. Makes sense, right? Crank up the brightness. Get faster electrons. But that's not what happened. What Lenard found was that the speed of the ejected electrons didn't depend on brightness at all. It depended on the color of the light, on its frequency. Shine dim violet light on the metal, and you'd get fast electrons. Shine blindingly bright red light, and you might get no electrons at all. Zero. No matter how intense the red light was, no matter how long you left it on, nothing happened. But even the faintest violet light would kick electrons out immediately. This made absolutely no sense in the wave picture. If light is a continuous wave washing over the metal surface, then more intensity should always mean more energy. It's like saying you could stand in front of a fire hose and not get pushed back, but a single drop of water from an eyedropper would knock you off your feet. The classical prediction was just wrong. Einstein's explanation, published in March of 1905, was breathtakingly simple. He said, what if light itself comes in quanta? What if a beam of light isn't a continuous wave at all, but a stream of individual energy packets, what we now call photons, each one carrying an amount of energy determined by its frequency, exactly as Planck's formula described. Each photon carries energy equal to Planck's constant times the frequency. One photon hits one electron. If that single photon carries enough energy to overcome the binding force holding the electron in the metal, the electron escapes. If it doesn't, nothing happens, no matter how many low-energy photons you throw at it. 1,000,000 photons of red light, each one individually too weak, will never do what a single photon of ultraviolet light can do. Think about that for a second. It's like a locked door that requires a key turned with a certain minimum force. You could press gently on the key 1,000 times, and the lock would never turn. But one firm twist, and it opens. The energy has to arrive in a single sufficient packet. That's quantization. That's the graininess of nature showing up in the most direct, observable way. And this was radical. Really radical. Because Maxwell's wave theory of light wasn't some tentative hypothesis. It was one of the great triumphs of 19th century physics. Hertz had confirmed it experimentally. It explained interference, diffraction, polarization, everything about how light behaves as a wave. And now Einstein was saying that light is also, somehow, a particle. Not instead of a wave, also a particle, both at the same time. This was the beginning of wave-particle duality, one of the deepest and strangest ideas in all of physics. And we are going to sit with it for a while, because it deserves that. But first, let me tell you about 1905, because what Einstein did that year is almost hard to believe. In the span of a few months, working in his spare time while holding down a full-time job evaluating patent applications, he published 4 papers that each would have been career-defining on its own. The photoelectric effect paper, which we just talked about. A paper explaining Brownian motion, the random jiggling of tiny particles suspended in fluid, which provided some of the first direct evidence that atoms are real, physical objects, and not just a useful theoretical fiction. A paper introducing special relativity, which completely reimagined the relationship between space and time. And a short follow-up deriving the most famous equation in physics, E equals mc squared, showing that mass and energy are the same thing, interchangeable, related by the speed of light squared. 4 papers, 1 year, a patent clerk. It's one of those stories that almost sounds made up, but it happened. And the thread that connects at least 2 of those papers, the photoelectric effect and Brownian motion, is this deep question about what matter and energy really are at the smallest scales. Are they continuous or discrete, smooth or grainy? And the answer, increasingly, was grainy. Atoms are real. Photons are real. The world is made of countable things. Now, Einstein's photon idea was not immediately accepted. In fact, it was resisted for years, even by people who respected him. Planck himself thought Einstein had gone too far. Niels Bohr, who would become one of the architects of quantum mechanics, initially rejected the photon concept. The wave theory of light was just too successful, too well confirmed to be thrown out. And they were right to be cautious, in a way, because the wave theory wasn't wrong. It was incomplete. Light really does behave as a wave in many experiments. It also really does behave as a particle in others. Both descriptions are necessary, and neither alone is sufficient. That's wave-particle duality, and it would take another 20 years before physics developed a framework that could hold both truths at the same time without contradiction. But let's stay in this period for a moment, because something beautiful is happening. The early 20th century is this extraordinary time when the very concept of what holds reality together is being dismantled and rebuilt, piece by piece, by a small group of people who are mostly quite young and who are arguing with each other constantly. And the next big piece of the puzzle comes from an unexpected direction, from the study of atoms themselves. By 1910 or so, people knew atoms existed. Dalton's atomic theory, Brownian motion, the periodic table, the evidence was overwhelming, but nobody knew what an atom looked like on the inside. The leading model was one proposed by J.J. Thomson, who had discovered the electron in 1897. Thomson imagined the atom as a sort of uniform blob of positive charge with electrons embedded in it, like raisins in a pudding. The British actually called it the plum pudding model, which is a delightful name for a scientific theory. It seemed reasonable. Electrons were known to be negatively charged and very light. The rest of the atom's mass had to be positive, so maybe it was all just mixed together evenly. And then Ernest Rutherford blew that picture apart. Rutherford was a New Zealander working in Manchester, England. A big, loud, energetic man, the kind of person who filled a room. He'd already won the Nobel Prize in Chemistry in 1908 for his work on radioactivity, which slightly annoyed him because he considered himself a physicist. In 1909, he sent two of his researchers, Hans Geiger and a young undergraduate named Ernest Marsden, to work on an experiment that seemed almost routine. They were firing alpha particles, which are basically helium nuclei, tiny, dense, positively charged projectiles, at a thin gold foil, and observing how the particles scattered. If Thomson's plum pudding model was right, the alpha particles should have passed through the foil with only slight deflections. The positive charge was supposed to be spread out evenly, so there would be nothing dense enough to cause a major deflection. And most of the alpha particles did pass straight through or close to it. But some of them, a tiny fraction, bounced back at large angles, and a few came almost straight back toward the source. Rutherford's reaction is one of the most quoted lines in the history of physics. He said it was as if you fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. It was, he said, quite the most incredible event that had ever happened to him in his life. Those words carry real astonishment, even across a century. Because what those rebounding alpha particles meant was that almost all the mass and all the positive charge of the atom was concentrated in a tiny, incredibly dense core, what Rutherford called the nucleus. The atom was mostly empty space. The electrons were orbiting far away, like planets around a distant sun, and the nucleus was unimaginably small compared to the atom as a whole. If the atom were the size of a football stadium, the nucleus would be a marble sitting on the 50-yard line. This was thrilling, but it was also immediately a problem. Because classical physics, good old reliable classical physics, said this couldn't work. An electron orbiting a nucleus is a charged particle undergoing acceleration. And according to Maxwell's equations, an accelerating charge radiates electromagnetic energy. So a classical orbiting electron should be continuously losing energy, spiraling inward, radiating light at ever-increasing frequencies, and crashing into the nucleus in a tiny fraction of a second. Every atom in the universe should collapse almost instantly. Obviously, atoms don't collapse. You're lying here right now made of atoms that have been stable for billions of years. So something was deeply, fundamentally wrong with the classical picture. And this is where a young Danish physicist named Niels Bohr enters the story, and the quantum revolution takes its next giant step. Bohr arrived in Manchester in 1912 to work with Rutherford, and he brought with him an audacious idea. An idea that married Rutherford's nuclear atom with Planck's quantum hypothesis in a way that was half brilliant and half held together with tape and hope. What Bohr proposed was that electrons don't just orbit the nucleus anywhere they please. They can only exist in certain specific orbits, certain fixed distances from the nucleus, and while they're in one of those orbits, they simply don't radiate energy. They just don't. He couldn't fully explain why. He just declared it as a postulate, a rule of the game. An electron in an allowed orbit is stable, period, end of discussion. And if you want the electron to move from one orbit to another, it has to make a quantum jump. It leaps from one allowed orbit to a different one, and when it does, it either absorbs or emits a photon whose energy exactly matches the difference between those two orbits. Think about what that means for a second. In the classical picture, an electron could orbit at any distance, any energy, smooth and continuous. Bohr said no. The electron is like someone on a staircase, not a ramp. You can stand on the first step or the second step, but you can't hover between them. And when you jump from the third step to the first, you release a specific, precise amount of energy, a photon with a very particular wavelength. That's why atoms emit light at only certain specific colors, certain spectral lines. Hydrogen, for instance, has that beautiful series of emission lines that had been measured with exquisite precision for decades. The Balmer series in the visible spectrum, and other series in the ultraviolet and infrared. Physicists had known about these lines since the 1880s. Johann Balmer had even found a simple mathematical formula that predicted their wavelengths, but nobody knew why the formula worked. It was just a pattern, a numerical coincidence hanging in midair without any physical explanation. And then Bohr's model came along and derived Balmer's formula from first principles. That was the knockout punch. When Bohr worked through the math, combining Planck's quantization condition with Coulomb's law for the electrical attraction between the proton and the electron, and the classical mechanics of circular orbits, he got an expression for the allowed energy levels of hydrogen. And when he calculated the wavelengths of photons emitted during transitions between those levels, out popped Balmer's formula. Exactly. The numerical constant in Balmer's equation, which had just been an empirical number, now had a derivation in terms of fundamental constants. The mass of the electron, the charge of the electron, Planck's constant. It was breathtaking. Einstein reportedly said that Bohr's work was one of the greatest discoveries ever made. And remember, Einstein was not a man who threw around superlatives carelessly. But here's the thing, and Bohr himself knew this. The model was a strange hybrid. It used classical physics when convenient and quantum rules when classical physics gave the wrong answer. There was no deep justification for why only certain orbits were allowed. Bohr essentially said, "These are the rules, and they give the right answers, and I can't yet tell you why." It was a placeholder, a brilliant, spectacularly successful placeholder, but a placeholder nonetheless. It worked perfectly for hydrogen. One proton, one electron, the simplest atom there is. But when you tried to extend it to helium, with 2 electrons, the model started to struggle. And for heavier atoms, it got worse. Something more fundamental was needed. Now let's sit with this moment for a bit, because I think it's worth appreciating the psychological landscape of physics around 1913, 1914. You've got Planck's quanta from 1900, Einstein's photons from 1905, Bohr's atomic model from 1913. These stunning results that work, that match experiments, but that nobody can really explain at a deep level. The classical framework that had served physics so magnificently for 2 centuries is cracking in every direction. And then, of course, the world itself cracks. World War I erupts in 1914, and physics, like everything else, gets swept into the catastrophe. Henry Moseley, the young English physicist who had just done brilliant work using X-rays to determine atomic numbers, work that basically gave the periodic table its modern foundation, was killed at Gallipoli in 1915. He was 27 years old. It's one of those losses that makes you wonder what he might have contributed if he'd lived. Karl Schwarzschild, the German astronomer, worked out the first exact solution to Einstein's general relativity field equations while serving on the Russian front and died of illness there in 1916. Physics didn't stop during the war, but it was battered and diminished by it. After the war, though, the quantum revolution accelerated in the most extraordinary way. And to understand what happened next, you need to meet a few more people. First, there's Louis de Broglie, a French prince, literally an aristocrat, the Duc de Broglie, who in 1924 proposed something that sounds almost absurd when you first hear it. If light, which everyone had thought was a wave, also behaves as a particle, Einstein's photons, then maybe matter, which everyone thinks of as particles, also behaves as a wave. Maybe electrons have a wavelength. He worked out a simple relationship. The wavelength of a particle equals Planck's constant divided by its momentum. And here's what's wild. This wasn't just philosophy. It was a testable prediction. If electrons are waves, then they should exhibit wave-like behavior. They should diffract. They should create interference patterns. And in 1927, Clinton Davison and Lester Germer at Bell Labs in the United States, and independently, George Paget Thomson in Scotland, the son of J.J. Thomson, who had discovered the electron as a particle, demonstrated electron diffraction experimentally. The father discovered the electron is a particle. The son proved it's also a wave. Both won Nobel Prizes. You can't make this stuff up. So now everything is both a wave and a particle. Light, electrons, atoms, everything. This is wave-particle duality, and it's not just a quirky fact about quantum mechanics. It's the central mystery. It's the thing that tells you the universe at its most fundamental level does not work the way your everyday intuition suggests. You, lying there right now, are made of particles that are also waves. The wavelength is unimaginably tiny for something as massive as a human being. So tiny that wave effects are completely undetectable at your scale. But for an electron, the wavelength is comparable to the spacing between atoms in a crystal, and the wave nature dominates everything. Now, 1925 and 1926. This is it. This is the crescendo. Two different people, working independently, using completely different mathematical approaches, cracked the code of quantum mechanics almost simultaneously. And the fact that they arrived at the same destination by entirely different roads is one of the most beautiful things in the history of science. The first was Werner Heisenberg. He was 23 years old in 1925, working with Max Born in Göttingen, Germany. Heisenberg was suffering from terrible hay fever. There's a famous story about this. And he retreated to the rocky island of Helgoland in the North Sea to recover. And there, essentially alone, working through the nights, he developed a new mechanics for the quantum world. His approach was radical. He decided to build a theory using only quantities that could actually be observed, the frequencies and intensities of spectral lines, and to abandon any attempt to visualize what the electron was doing between observations. No orbits, no trajectories, just mathematical relationships between observable quantities. What he ended up with was a formalism based on arrays of numbers, matrices, though Heisenberg didn't initially recognize them as such. When he brought his work back to Born, it was Born who realized that Heisenberg had independently reinvented matrix algebra. Born, along with his student Pascual Jordan, helped formalize the theory into what became known as matrix mechanics. And here's a detail that captures something essential about this moment. When Heisenberg worked out the multiplication rules for his arrays, he discovered something disturbing. The order of multiplication mattered. If you multiplied quantity A by quantity B, you got a different result than multiplying B by A. In normal arithmetic, 3 times 5 equals 5 times 3. But in Heisenberg's quantum mechanics, the equivalent operation didn't commute. This non-commutativity wasn't a bug. It turned out to be the most important feature of the whole theory. It's directly connected to the uncertainty principle, which Heisenberg would formulate in 1927. The idea that certain pairs of physical properties, like position and momentum, cannot both be known precisely at the same time. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. This isn't a limitation of your measuring instruments, it's a fundamental property of nature itself. The universe, at its deepest level, has a built-in fuzziness that no amount of technological improvement can eliminate. But matrix mechanics was hard. The math was unfamiliar to most physicists. The physical picture was deliberately abstract, and many people found it deeply unsatisfying. They wanted something they could visualize, something that felt more like the physics they knew. Enter Erwin Schrödinger. He was older than Heisenberg, 38 in 1926, Austrian, a man of wide-ranging intellectual interests, and, it should be said, a complicated personal life. Where Heisenberg had stripped away all visualization, Schrödinger went in the opposite direction. Inspired by de Broglie's matter waves, he set out to find a wave equation for the electron, a differential equation that would describe how these matter waves evolve in space and time, the same way Maxwell's equations describe electromagnetic waves. And over Christmas of 1925 and into early 1926, during a holiday in the Swiss Alps, reportedly in the company of a woman who was not his wife, a detail that physicists love to mention, Schrödinger found his equation, the Schrödinger equation. If you've taken any physics course, you've seen it. It's arguably the most important equation in all of quantum mechanics. It describes a mathematical object called the wave function, usually written with the Greek letter psi, and this wave function contains, in principle, everything there is to know about a quantum system. When Schrödinger applied his equation to the hydrogen atom, out came exactly the same energy levels that Bohr had found, but now derived from a proper wave equation, not from ad hoc rules. And it could handle more complex atoms too. Physicists loved it. It was familiar. It used differential equations, which they'd been working with for 2 centuries. It felt like real physics. So now you had 2 apparently different theories of quantum mechanics, Heisenberg's matrix mechanics and Schrödinger's wave mechanics. They looked completely different. They used different math, different philosophy, different mental pictures, and yet they gave the same answers for every problem you could throw at them. Schrödinger himself proved in 1926 that the 2 formulations were mathematically equivalent, different languages describing the same underlying reality. This was later made rigorous by John von Neumann, the Hungarian-American mathematician who was, frankly, one of the most terrifyingly intelligent humans who ever lived. Von Neumann showed that both formulations were special cases of a more general mathematical framework involving what's called Hilbert space, an abstract, infinite dimensional space where quantum states live as vectors. And this is where things get philosophically deep in a way that physicists are still arguing about today. Because Schrödinger's wave function, this psi, what is it, actually? What does it represent physically? Schrödinger himself initially thought it described a real physical wave, that the electron was literally smeared out in space, spread like a cloud. But Max Born proposed a different interpretation in 1926, one that Schrödinger hated, but that became the standard view. Born said the wave function doesn't tell you where the electron is, it tells you the probability of finding the electron in a given location. Specifically, the square of the wave function's magnitude at any point gives you the probability density, the likelihood per unit volume that a measurement will find the particle there. The electron isn't smeared out. It's that our knowledge of where it will be found is described by a probability distribution. Before you measure, the particle doesn't have a definite position. It exists in a superposition of possibilities. And when you do measure, the wave function collapses. It snaps to a definite value. This was and remains profoundly unsettling. Einstein never accepted it. His famous objection, "God does not play dice," was aimed directly at this probabilistic interpretation. He believed there must be some deeper, deterministic layer underneath, hidden variables that quantum mechanics was simply failing to capture. Bohr disagreed vehemently. The debates between Einstein and Bohr at the Solvay conferences in the late 1920s are legendary. Einstein would propose thought experiments designed to show that quantum mechanics was incomplete, and Bohr would stay up all night finding the flaw in Einstein's argument, often using Einstein's own general relativity against him. It was intellectual combat at the highest level, conducted with mutual respect, but genuine philosophical stakes. And here's what makes this so remarkable for our story about what holds reality together. By 1927 or so, physicists had a mathematical framework, quantum mechanics, that could predict the behavior of atoms and subatomic particles with extraordinary accuracy. It explained why atoms are stable, why they emit light at specific wavelengths, how electrons behave in metals and semiconductors, why the periodic table has the structure it does. It worked. It worked better than anything had ever worked before. But what it meant, what it said about the nature of reality itself, was and is fiercely contested. The math tells you what will happen. It's strangely silent on what is happening when you're not looking. But the quantum revolution wasn't done yet. Because so far, everything we've talked about, Schrödinger's equation, Heisenberg's matrices, is non-relativistic. It doesn't account for Einstein's special relativity. And for electrons moving at speeds close to the speed of light, which they do inside heavy atoms, you need a quantum theory that's compatible with relativity. This is where Paul Dirac comes in. And the story of what he found is one of the most astonishing in all of physics. Dirac was a quiet, almost preternaturally reserved English physicist. There are wonderful anecdotes about his literal-mindedness and his economy with words. And in 1928, at the age of 25, he wrote down an equation that changed everything. He was trying to do something very specific. Find a quantum equation for the electron that was consistent with special relativity. Schrödinger's equation worked beautifully, but it treated time and space differently, the way Newtonian physics does, and Einstein had shown back in 1905 that time and space are woven together. They're not separate things. So any truly fundamental equation for the electron had to treat them on equal footing. Others had tried. There was already something called the Klein-Gordon equation, which was relativistic and quantum mechanical. But it had problems. It gave negative probabilities, which doesn't make any physical sense. A probability is supposed to be a number between 0 and 1. Negative probability is like saying there's a -30% chance of rain. It's nonsensical. So Dirac went looking for something better, and what he found was elegant in a way that still takes physicists' breath away. The Dirac equation is a first-order equation, meaning it involves only first derivatives, not second derivatives, in both space and time, which is what you need for it to play nicely with relativity. But to make that work mathematically, Dirac had to introduce something new. The wave function in his equation wasn't just a single number at each point in space. It was a four-component object, a kind of four-entry column of numbers, and the equation involved new mathematical objects called gamma matrices, 4x4 matrices, that had to satisfy very specific relationships with each other. Dirac essentially discovered that to marry quantum mechanics with special relativity for the electron, you needed the electron to have an internal structure that nobody had put in by hand. It just fell out of the math. And here's what's wild. Two of those four components described something already known: an electron with spin up and spin down. Spin had been discovered experimentally a few years earlier by Gaudsschmidt and Uhlenbeck in 1925, and it was this strange quantum property where the electron behaves as if it's rotating, even though it's a point particle, and the idea of a point spinning doesn't really make classical sense. Physicists had been bolting spin onto quantum mechanics as an extra assumption, something you just had to add because experiments demanded it. Dirac's equation didn't need spin added. Spin emerged naturally, automatically, as a consequence of combining quantum mechanics with relativity. Think about that for a second. The mere requirement that your theory respect both quantum mechanics and Einstein's special relativity forces the electron to have spin. It's not optional. It's not an add-on. It's built into the fabric of how space-time and quantum physics fit together. But those other two components, the third and fourth entries in that four-component wave function, those were mysterious. They seemed to describe an electron with negative energy. And negative energy states were deeply troubling, because in quantum mechanics, particles can transition to lower energy states. If there were states with arbitrarily negative energy, every electron in the universe should cascade down into them, radiating away infinite energy. The whole universe would be unstable. Everything would collapse. Obviously, that doesn't happen, so something was wrong. Or something was very, very interesting. Dirac thought about this for a while, and in 1930, he proposed something audacious. He said, what if all those negative energy states are already filled? What if there's a vast sea of electrons occupying every negative energy state, and because electrons are fermions, particles that obey the Pauli exclusion principle, meaning no two can occupy the same quantum state. Ordinary electrons can't fall into those states because they're already taken. This was called the Dirac sea, and it sounds strange, but it led to a prediction. If you pumped enough energy into the vacuum, into this invisible sea, you could knock one of those negative energy electrons up into a positive energy state. That would leave behind a hole in the sea. And that hole, Dirac realized, would behave like a particle with the same mass as the electron, but with positive charge. It would be, in every measurable way, a positively charged electron. At first, Dirac was cautious. He wondered if this hole might be the proton, which was the only known positively charged particle at the time. But the math was clear. The hole had to have the same mass as the electron, and the proton is nearly 2,000 times heavier. So Dirac was predicting a completely new particle, one that nobody had ever seen. This was 1931. And then, in 1932, Carl Anderson at Caltech was studying cosmic rays using a cloud chamber, a device where charged particles leave visible trails of condensation as they pass through. And he photographed a particle that curved the wrong way in a magnetic field. It had the mass of an electron, but positive charge. He called it the positron. Dirac's equation had predicted the existence of antimatter, and the universe had confirmed it. Let that sink in. A 25-year-old, sitting quietly with pencil and paper, trying to make two theories mathematically consistent, discovered that the universe must contain a mirror version of matter, not because anyone had seen it, not because any experiment hinted at it, because the math demanded it, and the math was right. This is one of those moments where you really have to step back and marvel at the unreasonable effectiveness of mathematics in describing reality. The equation knew something about the universe that no human had ever observed. Now, the Dirac sea picture was eventually replaced by a more sophisticated framework, quantum field theory, which we'll get to. But the core prediction stood. Every particle has an antiparticle. Electrons have positrons. Protons have antiprotons, discovered in 1955 at Berkeley. Neutrons have antineutrons. When a particle meets its antiparticle, they annihilate each other, converting their entire mass into energy according to Einstein's E equals mc squared. This is real. It happens in medical PET scanners, positron emission tomography. The positrons emitted by a radioactive tracer in your body annihilate with electrons in your tissue, producing pairs of gamma rays that detectors pick up to create an image. Antimatter isn't science fiction. It's medical technology. It's inside you right now, in a sense, because certain radioactive isotopes of elements in your body occasionally produce positrons. But Dirac's equation, magnificent as it was, also pointed toward a deeper problem. Because once you combine quantum mechanics with special relativity, you can't really think of particles as fixed, permanent objects anymore. Relativity says energy and mass are interchangeable. Quantum mechanics says energy fluctuations happen all the time, especially on short timescales. That's related to the uncertainty principle, which connects uncertainty in energy with uncertainty in time. Put those together, and you get a universe where particles can pop into existence and vanish again, where the vacuum itself is a seething, frothing sea of virtual particles flickering in and out of reality. The number of particles isn't even fixed anymore. You need a framework where particles can be created and destroyed, where fields are the fundamental objects, and particles are just excitations of those fields. Little ripples, little quanta of energy in an underlying field that permeates all of space. This is quantum field theory, and it's the language in which modern physics describes everything that holds reality together. The idea started coming into focus in the late 1920s and 1930s, building on work by Dirac, Jordan, Heisenberg, Pauli, and others. The basic concept is beautiful and worth sitting with. Imagine a field, not a meadow, but a physical field, like the electromagnetic field, spread out across all of space. At every point, this field has a value, and that value can fluctuate. In classical physics, the electromagnetic field is smooth and continuous. It's what Maxwell described. But in quantum field theory, you apply the rules of quantum mechanics to the field itself. You quantize it, and when you do that, the quantized excitations of the electromagnetic field turn out to be photons. Photons aren't little bullets flying through space. They're ripples in the quantum electromagnetic field. Similarly, there's an electron field spread throughout all of space, and electrons are quantized, excitations of that field. There's a quark field, a neutrino field, a Higgs field, one for each type of fundamental particle. The universe, at its deepest level, is a collection of quantum fields layered on top of each other, and everything you see, everything you touch, everything you are, is patterns of excitation in those fields. Here's the thing that makes this so powerful. Because the fields exist everywhere, and because quantum mechanics allows energy fluctuations, particles can be created anywhere there's enough energy. Slam two protons together at nearly the speed of light, and the energy of their collision can excite various fields, creating new particles, Higgs bosons, top quarks, whatever the energy budget allows. The particles don't come from inside the protons. They come from the fields themselves, excited by the collision energy. It's like striking a drum and getting a sound. The sound wasn't hiding inside the drum. It was a vibration that the drum's surface could support, brought into existence by the energy of the strike. But quantum field theory had a terrible growing pain. When physicists tried to calculate things, like the probability that two electrons scatter off each other, or the magnetic moment of the electron, they kept getting infinity. Not just big numbers, infinity. The calculations would blow up because virtual particles at every energy scale contributed to the answer. And when you summed over all possible energies, the sum diverged. This was a crisis. You had a framework that was conceptually beautiful, that predicted antimatter and particle creation, and all these verified phenomena, but when you tried to extract precise numbers, you got nonsense. The resolution came in the late 1940s, and it's one of the great intellectual achievements of the 20th century. It's called renormalization, and the key figures were Shinichiro Tominaga in Japan, Julian Schwinger at Harvard, and Richard Feynman at Cornell. Three very different personalities who independently found ways to tame the infinities. Tominaga had actually done much of his work during World War II, isolated from the Western physics community, which makes his achievement all the more remarkable. Schwinger was a prodigy who gave dense, masterful lectures and produced calculations of extraordinary technical virtuosity. And Feynman, well, Feynman was Feynman. He developed an entirely new way of thinking about quantum field theory using what are now called Feynman diagrams, those little pictures with lines and vertices that represent particles interacting. They look deceptively simple, like doodles, but each diagram corresponds to a precise mathematical expression, and they revolutionized how physicists calculate. The basic idea of renormalization is subtle, but worth trying to grasp. The infinities arise because the theory, in its raw form, includes contributions from virtual particles at arbitrarily high energies. Energies so extreme that we have no idea what physics actually looks like there. Renormalization is a systematic procedure for absorbing those infinities into the measured values of quantities like the electron's mass and charge. You essentially say, I don't know what the bare mass and charge of the electron are at infinite energy, and I don't need to. I'll define my theory in terms of the mass and charge I actually measure in the lab and express everything else relative to those. When you do this carefully, all the infinities cancel, and you're left with finite, precise, testable predictions. And those predictions are staggeringly accurate. The magnetic moment of the electron, for instance, a quantity called the anomalous magnetic moment, or G-2, has been calculated in quantum electrodynamics to something like 10 decimal places and measured experimentally to comparable precision, and they agree. It's often cited as the most precise agreement between theory and experiment in all of science. 10 decimal places. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. This is quantum field theory flexing, showing you what it can do when the math is done right. Freeman Dyson, a young British mathematician who had moved to America, showed in 1949 that the approaches of Tominaga, Schwinger, and Feynman were all mathematically equivalent, different languages for the same physics. This was crucial because Feynman's diagrams were so much easier to use in practice that they quickly became the standard tool. But knowing that all three approaches agreed gave the whole enterprise a solidity it needed. Quantum electrodynamics, QED as it's called, became the prototype for all subsequent quantum field theories. It described how electrons and photons interact, and it did so with a precision that bordered on the absurd. But electromagnetism is only one of the forces that hold reality together. There's also the strong nuclear force, which binds quarks together inside protons and neutrons and holds the atomic nucleus together against the enormous electromagnetic repulsion of all those positively charged protons crammed into a tiny space. And there's the weak nuclear force, which is responsible for certain types of radioactive decay. It's what allows a neutron to transform into a proton, emitting an electron and an anti-neutrino in the process. Both of these forces needed their own quantum field theories, and building those theories was the great project of particle physics from the 1950s through the 1970s. The story of how that happened involves a cast of characters every bit as fascinating as the quantum pioneers, and it begins with a question that seems almost philosophical. Why do certain particles that seem so different on the surface behave in almost identical ways when you look at them through the right lens? Protons and neutrons, for instance. They have different electric charges, sure. The proton is positive, the neutron is neutral. But when it comes to the strong nuclear force, they're nearly interchangeable. They have almost the same mass. They bind together in nuclei following eerily similar rules. It's as if they're two versions of the same thing, just wearing different hats. And that observation, that sneaking suspicion that nature was hiding a deeper symmetry beneath the apparent diversity of particles, turned out to be one of the most powerful guiding ideas in all of 20th century physics. The person who first formalized this intuition was Werner Heisenberg. Yes, the same Heisenberg from the uncertainty principle, still making trouble. Back in 1932, right after the neutron was discovered by James Chadwick, Heisenberg proposed that the proton and neutron could be thought of as two states of a single particle, which he called the nucleon. The mathematical framework he used to describe this was something called isospin symmetry, borrowing the mathematics of spin, that intrinsic angular momentum we talked about, and applying it in a completely abstract internal space. It wasn't about anything literally spinning. It was about the mathematical structure, the way you could rotate between protonness and neutronness using the same kind of algebra that describes rotations in ordinary space. Now, this might sound like a cute mathematical trick, but it was pointing at something profound. It was saying that the strong force doesn't care about the difference between protons and neutrons. To the strong force, they're the same particle. The difference only shows up when you turn on electromagnetism, because electromagnetism does care about electric charge. So here's this hierarchy emerging. A deeper symmetry that's slightly broken by one of the other forces. And that pattern, deep symmetry slightly broken, turns out to be everywhere in particle physics. It's practically the leitmotif of the whole Standard Model. Through the 1950s and into the 1960s, experimentalists were smashing particles together in accelerators of increasing power, and the zoo of known particles just kept growing. It was bewildering. You had pions, kaons, lambda particles, sigma particles, xi particles, and more. Dozens of supposedly fundamental particles, each with its own mass, charge, spin, and various quantum numbers that physicists had invented just to keep track of which ones could transform into which. Murray Gell-Mann, working at Caltech, and independently Yuval Ne'eman, an Israeli physicist who was also a military intelligence officer, which is one of those biographical details that's too good not to mention. Both noticed in 1961 that these particles could be organized into beautiful geometric patterns based on their quantum numbers. Gell-Mann called his scheme the Eightfold Way, a playful nod to Buddhism, and the patterns looked like hexagons and triangles when you plotted the particles according to their properties. Here's what's really clever about this. The Eightfold Way wasn't just a filing system, it was predictive. Gell-Mann noticed a gap in one of his patterns, a spot where a particle should exist but hadn't been observed yet. He predicted its properties, its mass, its charge, its spin, its strangeness. That's actually a real quantum number, by the way, called strangeness, which tells you something about how many strange quarks a particle contains, though nobody knew about quarks yet. He predicted all of this, and in 1964, a team at Brookhaven National Laboratory found exactly that particle, the omega- baryon, with exactly the properties Gell-Mann had predicted. It was a Mendeleev moment, like predicting a missing element from the periodic table. The patterns were real, and they were telling you something about a deeper structure. And what was that deeper structure? Quarks. Gell-Mann proposed them in 1964, and so did George Zweig independently, though Zweig called them aces. The idea was that all those dozens of particles, the protons, neutrons, pions, kaons, all of them, weren't truly fundamental. They were built from smaller constituents, quarks, which came in 3 types or flavors: up, down, and strange. A proton was 2 up quarks and a down quark. A neutron was 2 down quarks and an up quark. The various mesons and baryons were different combinations of quarks and antiquarks, and suddenly the whole zoo made sense. The Eightfold Way patterns emerged naturally from the mathematics of combining 3 flavors of quarks. But here's the thing, and this bothered people for years. Nobody could find a free quark. You could smash protons together as hard as you wanted, and you'd produce showers of particles, but never a lone quark wandering around on its own. Every quark was always locked up inside some larger particle. This was deeply strange. Every other force gets weaker with distance. Electromagnetism, gravity, they all fade as you pull things apart. But the strong force apparently does the opposite. It gets stronger as you try to pull quarks apart, like a rubber band that gets tighter the more you stretch it. At some point, there's so much energy stored in that stretching that the energy itself converts into new quarks and antiquarks. Remember, E equals mc squared. Energy can become mass, and you end up with new particles instead of free quarks. This phenomenon is called confinement, and it's one of the most remarkable features of the strong force. The quantum field theory that describes the strong force is called quantum chromodynamics, or QCD, and it was developed through the late 1960s and 1970s by a number of physicists, with crucial contributions from Harald Fritzsche, Gell-Mann, and Heinrich Leutwiler. The name comes from the fact that quarks carry a type of charge called color. Not actual color, obviously, but a 3-valued charge that was whimsically labeled red, green, and blue. The force carriers of QCD are called gluons, analogous to how photons carry the electromagnetic force, but with a critical difference. Photons are electrically neutral. They carry the electromagnetic force, but don't themselves feel it. Gluons, on the other hand, carry color charge. They feel the strong force themselves. This means gluons interact with each other, not just with quarks, And that self-interaction is what makes QCD so much more complicated and so much richer than QED. It's what gives rise to confinement. It's why the strong force behaves so differently from electromagnetism. And then there's the weak force, which has its own strange and wonderful story. The weak force is responsible for beta decay, that process where a neutron turns into a proton, spitting out an electron and an antineutrino. Enrico Fermi had written down a rough theory of this back in 1933, treating it as a direct four-particle interaction, four fermions meeting at a single point. It worked reasonably well at low energies, but everyone knew it couldn't be the final answer because it produced nonsensical infinities at high energies. And unlike in QED, these infinities couldn't be tamed by renormalization. The theory was, in the jargon, non-renormalizable. Something was missing. What was missing turned out to be the force carriers. Just as the electromagnetic force is mediated by photons and the strong force by gluons, the weak force needed its own mediating particles. But there was a problem. The photon is massless, and that's intimately connected to the long range of electromagnetism and to the mathematical structure that makes QED renormalizable. If the weak force carriers were also massless, the weak force would be long-range like electromagnetism, which it obviously isn't. It only operates over incredibly short distances, smaller than an atomic nucleus. So the weak force carriers had to be massive. But simply giving mass to force-carrying particles by hand, just writing it into the equations, destroys the mathematical symmetry that makes the theory renormalizable. You're stuck. You need massive force carriers for the physics to work, but massive force carriers break the math. This is where one of the most beautiful ideas in all of physics enters the story. It's called spontaneous symmetry breaking, and the specific mechanism that makes it work in the Standard Model is associated with Peter Higgs, François Englert, and Robert Brute, along with independent work by Gerald Guralnick, Carl Hagen, and Tom Kibble, all published in 1964. The idea, loosely, is this. The underlying laws of physics can have a perfect symmetry, but the actual state of the universe, the vacuum, the ground state, the lowest energy configuration of everything, doesn't have to respect that symmetry. Think of a ball sitting on top of a perfectly symmetric hill. The hill is symmetric, but the ball has to roll down one side or the other, and whichever side it picks breaks the symmetry. The laws didn't change. The ball just had to choose. In the Standard Model, there's a field, the Higgs field, that permeates all of space, and it has settled into a state that breaks the symmetry between the electromagnetic and weak forces. Before this symmetry breaking, the electromagnetic and weak forces are actually aspects of a single unified force, called the electroweak force, described by a theory developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg in the 1960s and early 1970s. In the symmetric phase, all four force carriers, the photon and three weak bosons, are massless, and the theory is beautifully renormalizable. But the Higgs field breaks this symmetry, giving mass to three of the four force carriers, which become the W+, W-, and Z bosons, while leaving the photon massless. The electromagnetic force and the weak force, which look so different at everyday energies, are revealed to be two faces of the same coin, separated only by the Higgs field's choice of vacuum state. Gerard 't Hooft and Martinus Veltman proved in 1971 that this whole construction, the electroweak theory with spontaneous symmetry breaking, was indeed renormalizable. You could calculate with it. You could make predictions. And the predictions were confirmed spectacularly in 1983, when the W and Z bosons were discovered at CERN by Carlo Rubbia and Simon van der Meer's team, with masses almost exactly where the theory said they'd be. The W bosons weighed in at about 80 gigaelectronvolts, the Z at about 91 gigaelectronvolts, roughly 80 and 90 times the mass of a proton. These are heavy particles, which is why the weak force has such a short range. It takes a lot of energy to create them, even as virtual particles, so they can only flicker into existence for the briefest of instants, carrying the force over the tiniest of distances. So by the mid-1980s, the picture had come together into what we now call the Standard Model of Particle Physics. 3 forces, electromagnetic, strong, and weak, each described by a quantum field theory built on principles of symmetry. The electromagnetic and weak forces unified into the electroweak theory. Matter built from quarks and leptons, the leptons being particles like the electron and neutrino that don't feel the strong force. 6 quarks in total: up, down, strange, charm, bottom, and top, the last of which wasn't discovered until 1995 at Fermilab, weighing as much as an entire atom of gold. 6 leptons, the electron, muon, and tau, each with its own neutrino. Force carriers, the photon, 8 gluons, and the W and Z bosons. And the Higgs boson, the quantum of the Higgs field, whose discovery at CERN in 2012 was the final piece of the puzzle, the last particle predicted by the Standard Model to be experimentally confirmed. And here's what's genuinely astonishing about this framework. It works. It works to a degree that is almost unreasonable. Every experiment we've done, every particle we've smashed, every decay rate we've measured, every cross-section we've calculated, the Standard Model gets it right. Sometimes to 10, 12 decimal places. It is, by any measure, one of the most successful scientific theories ever constructed. It tells you what everything is made of and how it holds together, from the quarks inside a proton, to the nuclear reactions that power the sun, to the reason a neutron can decay into a proton and keep the chains of nucleosynthesis going that built every atom in your body. But, and you probably felt this coming, it's not complete. It can't be, because there's something enormous that the Standard Model simply leaves out, something so fundamental that its absence is almost embarrassing. And that something is gravity, the oldest force we know about, the one Newton described, the one Einstein reimagined as the curvature of space-time itself. The Standard Model has nothing to say about it. Gravity just sits there, outside the framework, described by general relativity in a completely different mathematical language, operating by completely different rules. And the question of how to bring gravity into the quantum fold, how to write down a quantum field theory of gravity that actually works, that doesn't blow up with uncontrollable infinities, that question is one of the deepest unsolved problems in all of physics. And it's worth sitting with for a moment, because the nature of the difficulty is genuinely fascinating. It's not just that nobody's been clever enough yet. It's that the two frameworks, quantum field theory and general relativity, seem to disagree about something fundamental about the nature of reality itself. Here's the thing. In quantum field theory, everything plays out on a stage. That stage is space-time. You set up your fields on a fixed background, flat Minkowski space-time usually, and you calculate how particles interact, how they scatter, how they decay. Space-time is the arena. It's rigid, it's given to you in advance. But in general relativity, space-time isn't the stage, it's one of the actors. Space-time itself is dynamic. It bends, it warps, it ripples. Matter tells space-time how to curve, and space-time tells matter how to move. as John Wheeler so beautifully put it. So when you try to write a quantum field theory of gravity, you're trying to quantize the very stage on which quantum field theory is supposed to take place. You're trying to make the arena itself subject to quantum uncertainty, to superposition, to fluctuation. And that's a conceptual tangle that goes far beyond just getting the math to work out. But people tried anyway. Of course they did. The most straightforward approach: just treat gravity like the other forces, write down a quantum field theory with a spin-2 force carrier called the graviton, and calculate, actually works fine at low energies. At long distances, for weak gravitational fields. You can do quantum gravity calculations for everyday situations, and they give perfectly sensible answers. The trouble comes when you push to high energies, short distances, extreme conditions. When you try to calculate what happens at the Planck scale, roughly 10 to the minus 35 meters, or energies around 10 to the 19 GeV, the theory falls apart. The infinities that show up in your calculations can't be absorbed by renormalization the way they can in QED or QCD. Every time you try to cancel one infinity, you need to introduce a new parameter, and then another, and another, an infinite number of them. The theory loses all predictive power. It's not that you get wrong answers. You get no answers. The mathematical machinery just grinds to a halt. And that scale, the Planck scale, is absurdly tiny. We're talking about distances roughly 100 billion times smaller than a proton. No experiment we can currently build comes anywhere close to probing it. So in one sense, this isn't a practical problem. For anything you'd actually want to calculate in the real world, the orbit of a planet, the bending of light around a galaxy, the behavior of particles in a collider, either general relativity or quantum field theory, works just fine on its own. The problem is conceptual. It's about consistency. It's about the fact that nature presumably doesn't use two incompatible rulebooks. There has to be some deeper framework from which both emerge, and there are places in the universe where this isn't just academic. Black holes, for instance. At the center of a black hole, general relativity predicts a singularity, a point of infinite density where the curvature of space-time becomes infinite. That's the theory telling you it's broken, that it's being pushed beyond its domain of validity. To understand what actually happens at the center of a black hole, you'd need a quantum theory of gravity. Similarly, the very earliest moments of the Big Bang, the first tiny fraction of a second, when the entire observable universe was compressed into a region smaller than an atom, that's another place where both quantum mechanics and gravity matter simultaneously, and neither theory alone can tell you the full story. So people have been working on this for decades, and the two most prominent approaches are probably string theory and loop quantum gravity, though there are others. Let's talk about them, gently, because even the basic ideas are kind of beautiful. String theory emerged in a somewhat accidental way. It actually started in the late 1960s as an attempt to understand the strong force, before QCD came along. Gabriele Veneziano, an Italian physicist working at CERN, wrote down a mathematical formula in 1968 that seemed to describe certain patterns in how strongly interacting particles scattered off each other. It was a strange formula. It used a mathematical function that Euler had studied 200 years earlier, and for a while, nobody was quite sure what physical picture it corresponded to. Then, in 1970, Yoichiro Nambu, Holger Beck-Nielsen, and Leonard Susskind independently realized that Veneziano's formula could be interpreted as describing not point particles, but tiny, one-dimensional vibrating strings. Different vibration modes of the string would correspond to different particles, the way different vibration modes of a guitar string produce different notes. Now, as a theory of the strong force, string theory was quickly superseded by QCD, which worked much better. But then, something remarkable happened. When people studied the mathematics of these vibrating strings more carefully, they found that one of the vibration modes automatically produced a massless spin-2 particle, and a massless spin-2 particle is exactly what a graviton would be. The theory was predicting gravity whether you asked for it or not. John Schwartz and Joel Shirk pointed this out in 1974, and they made a bold suggestion. Maybe string theory isn't a theory of the strong force at all. Maybe it's a theory of everything, including gravity. The idea lay somewhat dormant for about a decade, because there were technical problems. The theory seemed to predict particles that traveled faster than light, and it required extra dimensions of space beyond the three we see. But in 1984, Schwartz and Michael Green showed that a particular version of string theory was free of certain mathematical inconsistencies, called anomalies, and suddenly the field exploded, the so-called first superstring revolution. Within months, thousands of physicists pivoted to working on string theory. Edward Witten, widely considered one of the greatest mathematical physicists alive, became one of its most powerful advocates. The promise was intoxicating. A single framework that would unify all four forces, explain why the particles of the Standard Model have the masses they do, resolve the singularities of black holes, and give a consistent quantum description of gravity. And string theory has produced some genuinely profound results. One of the most celebrated came from Andrew Strominger and Qumran Vafa in 1996, when they used string theory to calculate the entropy of a particular type of black hole and got exactly the answer that Stephen Hawking and Jacob Bekenstein had predicted decades earlier using semi-classical arguments. That was a stunning confirmation that string theory was capturing something real about quantum gravity. Juan Maldacena's ADS/CFT correspondence, proposed in 1997, suggested a deep and precise equivalence between a gravitational theory in a certain curved spacetime and a quantum field theory without gravity living on the boundary of that spacetime. It's one of the most influential ideas in theoretical physics in the last 30 years, and it's generated insights that flow in both directions, using gravity to understand strongly coupled quantum systems and using quantum field theory to understand aspects of gravity. But here's the honest picture. String theory, for all its mathematical beauty, has not yet made a single testable prediction that distinguishes it from the Standard Model plus general relativity. The extra dimensions it requires, 6 or 7 of them, depending on the version, would need to be curled up so small that we can't detect them, and the number of ways they can be curled up is staggeringly large. Some estimates put it at 10 to the 500 different possible configurations, each giving rise to a different low-energy physics. That's a landscape of possibilities so vast that critics argue the theory can accommodate almost any observation, which means it predicts almost nothing specific. This has been a source of deep frustration and genuine controversy within the physics community. Is string theory a theory of nature, or is it an incredibly rich mathematical structure that might describe many possible universes but doesn't pin down ours? Loop quantum gravity takes a very different approach. Instead of adding new ingredients like strings and extra dimensions, it tries to quantize gravity directly, using the mathematics of general relativity itself. The key idea, developed primarily by Abhay Ashtekar, Carlo Rovelli, and Lee Smolin starting in the late 1980s, is that space itself has a discrete structure at the Planck scale. In loop quantum gravity, space is not a smooth continuum. It's woven from tiny, discrete chunks. Think of it like a fabric that looks smooth from a distance, but is actually made of individual threads if you zoom in close enough. The geometry of space, areas and volumes, comes in discrete quanta, just as energy comes in discrete quanta in ordinary quantum mechanics. The smallest possible area is roughly the Planck length squared, about 10 to the minus 70 square meters. Below that, the concept of area simply doesn't apply. It's a beautiful idea, and it has its own successes. Loop quantum gravity can resolve the singularity at the center of a black hole and at the Big Bang, replacing them with regions of extreme but finite curvature. In loop quantum cosmology, the Big Bang is replaced by a big bounce. The universe didn't emerge from nothing, but contracted from a previous phase and then bounced back out when quantum gravitational effects prevented the density from becoming infinite. But loop quantum gravity has its own challenges. It's been difficult to show that smooth classical spacetime emerges from the discrete quantum structure at large scales. And like string theory, it hasn't yet produced experimentally testable predictions that we can check with current technology. And honestly, there are other approaches too. Causal dynamical triangulations, which try to build spacetime from tiny simplex-shaped building blocks. Causal set theory, which proposes that spacetime is fundamentally a set of discrete points with only causal ordering between them. Asymptotic safety, which suggests that gravity might actually be renormalizable after all if you look at it the right way at a special fixed point of the renormalization group flow. Each of these has its own elegance, its own insights, its own community of brilliant people pushing the ideas forward. None of them has won yet. And then there are the other great mysteries that the Standard Model leaves unanswered, even setting gravity aside. Dark matter, something that makes up about 27% of the energy content of the universe that we can see through its gravitational effects on galaxies and galaxy clusters, but that doesn't correspond to any particle in the Standard Model. Dark energy, the mysterious something that's causing the expansion of the universe to accelerate, making up about 68% of the total energy budget, and about which we understand almost nothing. The matter-antimatter asymmetry. Why is the universe made of matter rather than antimatter when the laws of physics treat them almost identically? Neutrino masses. We know neutrinos have mass because they oscillate between flavors, but the Standard Model in its original form predicted them to be massless, and we still don't fully understand the mechanism that gives them their tiny masses. The hierarchy problem. Why is the Higgs boson so much lighter than the Planck scale when quantum corrections would naturally push its mass up to enormous values? These are real, concrete, unsolved problems, and they tell us something humbling and also, I think, deeply exciting. The Standard Model, for all its breathtaking success, is not the final answer. It's a way station, an extraordinarily precise and powerful way station, but a way station nonetheless. There's more structure underneath, more physics to be discovered, more of reality waiting to be understood. But let's step back for a moment, because I think it's worth appreciating, quietly, just how far we've come. Think about where we started tonight. The ancient Greeks sitting around arguing about whether everything was made of water or fire or some combination of earth and air. Democritus, imagining that if you cut something in half enough times, you'd eventually reach an uncuttable piece, an atom, and being dismissed for centuries because the idea seemed too radical, and then the slow, painstaking climb. Dalton figuring out that elements combine in fixed ratios, Faraday discovering that electricity and magnetism are deeply connected, that invisible fields permeate all of space, Maxwell writing down 4 equations that unified light, electricity, and magnetism into a single framework, Planck, reluctantly, desperately, introducing the quantum to save physics from the ultraviolet catastrophe, Einstein showing that light comes in packets, that mass is energy, that space and time are woven together, Rutherford firing alpha particles at gold foil and discovering that atoms are mostly empty space with a tiny, dense nucleus at the center, Bohr building his model of the atom, knowing it was wrong, but knowing it was pointing somewhere true, de Broglie imagining that electrons are waves, Heisenberg and Schrödinger working independently, building the mathematical machinery of quantum mechanics, Dirac unifying quantum mechanics with special relativity and predicting antimatter, and being right. The long, difficult development of quantum field theory, with its infinities and its renormalization, leading to QED's almost impossibly precise predictions. And then, the Standard Model coming together, piece by piece, over decades. The discovery of quarks, the understanding of confinement, the development of QCD, the electroweak unification, the Higgs mechanism. Each piece hard-won, each one the result of years of work by hundreds of people, theorists and experimentalists, often arguing fiercely, often getting it wrong before getting it right. And finally, in 2012, the Higgs boson appearing in the detectors at the Large Hadron Collider, confirming the last piece of the puzzle. That's the story of how we figured out what reality is made of and how it holds together. And it's a story that's still being written. Somewhere right now, someone is working on the next piece. Maybe they're scribbling equations on a whiteboard at 2 a.m, or running simulations on a supercomputer, or analyzing data from a detector buried deep underground. Maybe they're a graduate student who hasn't published their first paper yet. Maybe they're about to have the insight that changes everything. We don't know. That's the beautiful thing about it. The story isn't finished. But for tonight, you don't need to solve quantum gravity. You don't need to find the dark matter particle or explain the cosmological constant. You just need to rest, knowing that the universe, for all its strangeness, for all its unsolved mysteries, has a deep structure that we've been slowly uncovering for thousands of years, and that the picture we've built, fields vibrating, particles flickering in and out of existence, forces carrying energy across space, symmetries breaking and reshaping the rules. That picture is astonishingly, unreasonably, beautifully close to the truth. The same quantum fields that power the sun are humming quietly in every atom of the pillow under your head. The same electromagnetism that Maxwell wrote down on a page in the 1860s is holding every molecule of your body together right now. You are, quite literally, made of the stuff we've been talking about all this time. Quarks and electrons, bound by gluons and photons, shaped by the Higgs field, obeying rules that took us centuries to discover, but that have been running flawlessly since the first moments of the universe. And that's a pretty good thought to fall asleep to.